is the reflection. All right. Okay. Let me make sure I'm there. Let's see, I guess I'm there. Oh, yep. Okay. All right, let's see. Okay, I think I need to create another page and then head back here. Hello. I think 15 is the wrong one. Yeah, 16. Okay. So I'm probably going to talk about this for just a minute, and then what I'm going to do is just work a problem, because sometimes too much of this is kind of a waste, and it's maybe better to just work a problem. So the way he's written this out is if you have two objects, 2 points on a rigid body, each one can have its own path, but if they're a rigid body, they stay the same distance from each other unless they break, and then they're not a rigid body anymore. So what he's set up is a way to describe a position of some point A and then position of some point B. But if you happen to be sitting on A and looking at B, and it's a rigid body, the only thing you'll see is it rotating. If you're stuck on A, now you may be moving somewhere, but that's all you'll see. And so what he's written is, okay, so he's done a delta, but it really doesn't matter. It's basically, if you're sitting on A, you may be moving, but you may not know how you're moving. Someone probably could describe that. But if you're sitting on A and looking at B, all you see is a rotation about yourself. That's all you see. So in other words, now he gets into this mess here where he basically says, okay, so I might move from here to here, might move from here to here, and the fact that this distance this vector is not the same as that means the thing is rotating as well. No, it's okay. So it may have now this we won't use, but it'll have a d theta. Then he can go down, take its derivative. Well, he's taking the derivative now. And what he ends up with is, it's kind of weird, but not that weird. So you have the velocity at some point B is equal to the velocity at some point A plus the velocity of a person that's sitting on A looking at B. Now this one's only due to rotation about A. Now, what useful is that? Okay, so let's go a little bit further, and then I'll just take off and work a problem to show you how it's useful. So, he's setting it up for us. So, if you're sitting on A, looking at B, the only thing you see is rotation, which looks just like this. So omega cross r, and we talked about that last time, how that's actually a subset of the polar coordinates. So you get down here, and you basically can use the omega and use the r in order to find velocity A and B. So okay, now he's setting up this. Let me go down and just grab a problem and work it. Or I guess I could, well, there's examples here, but I think what I want to do is find a problem. Okay, let's see. Well, first thing he does is say set up the relative motion equation. I think I want to go further than that and actually, does he have better, these are preliminary problems, which are okay, but maybe he has a better set. Oh, I guess I'll do one of those. Here we go. Okay, hang on. I'm going to go further than just setting up the equations, because just setting it up is fine. Nothing wrong with that, but taking it all the way through the problem is actually better. Okay, so the key here is, I think I'm going to write the equations. I'm going to do like what he said first, and then write the equations, and then go and solve the equations. So, unfortunately, he did not label this one. He did label that point, and he did label this one. So I guess I'm stuck labeling this one a C. Now I'm going to go all the way through it. So this seems weird, but velocity of A is equal to the velocity of A relative to, now I write them like that. He actually trades these two places, but you know, because I can say it like that, A relative to C plus velocity of C. Now, I'm going to go ahead and go through, well, then I'll do one more step. Let's say velocity of A is equal to omega. If you look back at his equation, oh, yeah, a couple pages back. Come on. He actually should have one thing here that he doesn't have. And here, let's see if I put it on here. I don't know why. So, okay. So there's your equation. And he has an A and a B listed here. But actually, there could be several omegas in a problem. So he really needs to make sure that this is omega AB. So in other words, if you have something that's connected to A and B, and it's rotating around, you need to know the omega of that. And if you don't put a subscript and you have A connected to C over here, you might get confused. So you need AB and then say an omega of AC. So in my mind, this should have a little subscript, but that's okay. He's introducing it. So, and this is a vector across R, A to C, and one way to think about it is this subscript here is the same as that, and that just happens to be omega of the same length. Plus velocity of C. Now what I'm going to do is I'm going to go ahead and solve this, and then I'll go back and deal with the A and B. So what happens is, okay, there's an omega, but he has this represented as a vector form. And so the thing you need to be aware of is there is a coordinate system here, and if you look at your coordinate system like that, then you take your hand, put on the page, rotate your fingers towards Y from X to Y, and your thumb points up towards you, and that's the positive Z. So therefore, this is a positive omega. So that's kind of a standard. So let's see. That's counterclockwise. If X is going this way and Y is going that way, counterclockwise rotation is positive. And most people list that way. Most people do like this. They generally don't do this. So throughout everything, I'm going to stick to that. Okay, let me get this other stuff off here. So, that being the case, okay, in the textbook, he may, so here, I'll write it over here. Make it AC vector form minus 6K, because that's coming towards you. So, oh, I forgot to bring my water. So what you have is minus 6K cross, and I'll put it in parentheses, cross that. So if you draw a vector that originates from C and points to A, you'll have a vector that kind of just does like that. Bad drawing, but it's 3 meters long. So that, and it only points in the X. You have that. Now, luckily, for this particular case, this thing is pinned to the wall. Since it's pinned to the wall, it doesn't have any velocity. So the only velocity you have here, well, the velocity of A is that. Now, he'll go through the book and he'll see stuff like, oh, I cross J is equal to K and all that sort of stuff. To me, when I've seen people do that, I have seen people make a lot of mistakes. So what I like to do is list it in the old standard method like that, where I can take this and put it right here, and then take this one, put it right there, and then at this point I could say plus 0, because that's what that is. Then from here I can do a cofactor expansion. The reason I do that is just because I'm less prone to make mistakes that way. So if I do a cofactor expansion, I take the I, and I'll get that, put there, 0 minus 6, 0, 0. And then if I'm taking the J, I have to take the minus sign of it, and I build the matrix like that, minus J, 0 minus 6, 3, 0. And then if I take the K, I'm taking the K and do this out of it. Go right there. 0, 0, 3, 0. Now, okay, so if I go in here and look at this first one, that comes out 0, and that comes out 0, so I get nothing here. Minus J. Okay, that comes out 0. That comes out minus 18, but I gotta take the minus of the minus. So I get 18. Why did I put the bar there? That's supposed to be a parentheses. And then here, I get nothing times nothing. So I show that, alright, I've already forgotten. That velocity, that's velocity of A is equal to minus 18J. Now at this point, I should be able to verify that, just kind of semi by observation. And that is, I know if this thing were rotating this way, every point on it would be going straight down. So if you drew a straight line from there to there, say, okay, let's see. If I drew a straight line from there to there, okay, come on. And then got rid of the ruler, and all these points are rotating like that. That's the velocity of them, which is straight down, and that value should be 3 times 6. That's the value at the end, should be 3 times 6, or 18. And it's going down, and going down means it's going in the minus y direction there. So with that, I can just get rid of all this mess again. I don't think, I'm going to probably use the same picture to mess with it for a second. So there, I've got that. And that seems like a great thing, but somebody might actually be interested in finding out what the speed of this thing is, the velocity of b. That might be what they're interested in finding out. So I know in here he says just write the equations. Oh, I'm on the wrong place. He says just write the equations, but I think it's more instructive to write them and solve them. So he doesn't give me, hey, find the velocity of this or that. He just says write the equations. I'm going to go ahead and solve for the velocity. Well, I've already got the velocity A, so I want to solve for the velocity of B. So what I'm going to do is use this kind of thing here and just take this thing and slide it over here and go like so, and just unboxing it because it's its own entity, so to speak. So there's its own entity. But out of that, what I want to take with me is this. I want to take that with me. I guess if I'm taking it, I need to go up here and put it up here. Velocity of A is equal to minus 18 of J. And maybe I need to move it a little further to the right. I'm seeing that my handwriting might be too big. So I'm going to move it there. Okay, so now, in your mind, if you go in here and say, I no longer care about this link. Now I care about this link. And it's a rigid link, and A and B are on either end of it. So therefore, sorry, velocity of B is equal to velocity of B relative to A plus velocity of A. And then I can write one more step, omega AB cross R beta A plus velocity of A, which I actually have now. And here I probably should. I actually have that, and I can put that in there in a minute. I'm not going to worry about it for a minute. Now, if I just look at this and say, hey, what is this? And I don't know yet. Oh, I don't know that yet. Okay. However, since I don't know it, one of the things I always do is I always assume it's positive. So again, if you look at this, this is as if you're sitting on A and you're looking at B. So during this part of the computation, during this part, what your mindset should be this. Now let me see if I can, I'll go back and get a copy from the original. If I get a copy from the original, ooh, you know what? I think, okay, I don't want to do it this way. I want to do it this way. I don't know why it does differently when I do it this way, but you get the mode as a free form. And what I want to do, I just want to get this. Okay, so I go back over here, and in my mind, this is all I care about. So this is a weird way of thinking, but it actually is instructive in a way, because, okay, go ahead and move. So the reason it's instructive is staring at this and this, you could almost treat this during just this blue part of the calculation as if this thing is on here. I'll go ahead and put a coordinate system on it too. You don't have to, but here's my X, here's my Y, and let's say it's omega AB, of which I don't know what it is. So it's almost you sitting here on A during this part of the computation is I'm sitting on A looking at B. It is true I'm going down, but I don't know that. I'm not sure of that. So as I'm rotating, I kind of see, like, look at B and it looks like it's rotating about. So what I'm going to do is, here, I'm going to basically put my I, my J, and my K, 0, 0. I don't know what it is, so I'm going to just put it there. Now, what is RBA? That is a vector that goes like so. Bad drawing there, but I'm trying to make it look like an arrow. So what is that? So this is R drawn to B as if it came from A. Well, not as if, because it does come from A. And I got a component going that way and a component going that way. So they're both going in the opposite X and Y direction, so they're both negative. And I got 60 degree here, so I got 60 degree here, but it really doesn't matter. It's 2 meters long, and I'm going to do the X first. So it is cosine of 60I, and then the Y is going to be minus 2 sine of 60J. And unfortunately, it's too big. The writing's too big for me. So what I'm going to do, I'm going to do this. I can make it smaller and shove it to the left. That is larger. Now, I did not start octave. Okay, so I have done this in the past where I've paraphrased this, where I write it like minus 2C60, which means cosine 60, and then minus 2S60, J, which is sine 60. And I might do that for a second. So if I do that, the first thing is I need to move that over, and move this over. Let's all say minus 2 cosine 60 and minus 2 sine 60 and 0. And so I'm taking the determinant of that. So I take the I times the cofactor of this thing right here. And so it would be 0 omega A. It's supposed to be AB. I don't know what happened there. That's supposed to be AB right there. And minus 2 sine of 60 and 0 minus J, cofactor expansion of this part right here, put right here, 0 minus 2 cosine 60, make it AB, 0, and then this last one, okay, which, if you haven't noticed, every here, okay, we're reconnected. Minus, okay, go ahead. Minus 2 cosine 60 minus 2 sine of 60. That's always 0. So what I'll end up with is minus 2, okay, plus minus. Okay, this one is a plus sign and this is a minus sign. So since I got two minuses, I'll have 2 sine 60 omega AB I comes out of this. Okay, plus and a minus, that minus makes it a plus, and then another minus makes it a minus. 2 cosine 60 omega AB, and then I'll put a box in there. So, let's see. Now, I'm going to stop, and I'm going to make sure that this makes sense. And here's how I'm going to do this. I'm going to go back to the drawing. I'm going to kind of get rid of as much of this mess. If omega AB were rotating this way, and you were sitting here, and you were looking here, you would see this going in this direction. So, if that were the case, you would have a positive x component, and you would have a negative y component. And that's kind of what I see, a positive x and a negative y. Now, at this particular point, we checked and realized we have a positive and negative. We're okay there, but the values. And there's something really interesting here that you can do. There's the properties of vectors that make it so you can check the actual value. Now let me run you through that real quick. It sounds weird, but let's say you had a vector A and you had a vector B. And say they're just some value apart. So if you cross them, if you say A cross B, and that equals C. And believe it or not, C, okay, so this is just some arbitrary X, Y, and Z, three-dimensional vector. Then this would be your C. But what would happen out of this is this. Because of the properties of this thing, C would always be perpendicular to B, and it would also be always perpendicular to A. If it's perpendicular, then this means the result of a cross product, C, could be dotted with A, and the C could be dotted with B as well, and the definition, it would be this. Now, it would be cosine. Now, here's the key. They're both 90 degrees. So it would be cosine 90. C, magnitude of C, magnitude of B, cosine of 90. Again, why is it 90? Because this is part of the thing. When you cross two vectors, this vector will be orthogonal or 90 degrees to that one. It will also be 90 degrees to that one. If we look at cosine, you have this. Here's your 90 degrees. So guess what? The dot product always equals 0. Now, so if you take the result of a cross product and dot it with either one or both of the vectors that created it, it will give you a value of 0. Now let's use that as a check. Uh-oh. Yeah. Okay. Use it as a check, and what's funny, okay, so I guess I'll move this to the side in case I need to reference it later. I don't think I do, but here I'll just move it over here. So I'm looking at this as a result. This is my result of a cross product between those two. So therefore, if I were to dot this vector with either this or that, I should get 0. Now, wait a minute. I want to get rid of that. Okay, so let's do that. Now, it's kind of convenient that these vectors are sitting here in this little area here. Here's the x component, here's your y component, and here's your z component, and your z component. So if I do this, here's what's funny. Okay, here's my x component here. Here's my y component here. And then I'll do that as a mysterious plus 0 times k, because this will always be the case. So let's take off and do that. Okay. In a dot product, where you dot A dotted with B, all you do is AX times BX plus AY times BY plus AZ times BZ, and you just add them up. So that's how you do a dot product if you have the components. If you have them in a vector with the angle between them, that's the other way to do it. In other words, let me go back to this. If you have the angle between them, you can do that. If you don't have the angle between them, then you're saying A dot C would be CX AX plus CY AY plus CZ AZ. And that, believe it or not, that's going to be 0 if these vectors are 90 degrees apart. So let's head back and see. This is a check, and this is a way of, if I can find it again, this is a way of checking yourself along the way to know whether you got the right answer. So if we take this times that, and then this one times that one, and then this one times that one, will add up. We're going to check that one. Now, let's do the stupid one first here. Here's the stupid one. Here's what I mean by stupid. 0 times that, and then this times 0, and then this one times 0. That's pretty stupid, because the 0 times that gives you 0, that one gives you 0, that one gives you 0. That was not useful at all for a check. This one is useful. This times that, add that together with this times this, and add it together with this times this. Now the last one, this one always is 0. So if you stare at the one that comes out of the blue, well, let's look at the one that comes out of the blue here. You get a minus. I'll do the one on top. 2 sine of 60 times a minus 2 times cosine of 60 times omega AB. That is this number times that number. Now, let's do the other one. And over here, minus 2 cosine of 60. That's this one right here. And then take this one, put right there, 2 sine of 60, omega AB. And then you add these two together. Didn't take you long to realize, okay, this plus, this 2 minuses become a plus. You get 2 sine of 60. Get that. This. That. So in fact, this is 0. So not only does it check out on the drawing as being in the right direction, it also checks out mathematically. Now, it doesn't take you long to realize you can just do this. I mean, I did this where I wrote all these terms down. It doesn't take you long to realize that you can do this visually, because what happens is it's kind of weird, but you'll see this term end up right here, and you'll see this term end up right there. And it always is the case, but you got to check your signs to make sure they're that way. And so, just like that, okay, just like that, you can check it and make sure you got the right answer. So, visually, makes sense. If you are in fact sitting on A, it does appear like that's the direction it's going. Going a little bit to the right, a little bit down. You got your signs there. You go back here, you check it with the dot product, you'll say, hey, it's exactly right. So now where am I at now? Okay, so if I go back to the equation, I will now copy this all the way back down, and I'll say velocity of B is equal to. Now what I'll do is I'm going to take all this, all this, and put it down. So I'm going to put 2 sine of 60 omega AB I minus 2 cosine 60 omega AB J. And now guess what I'm going to do? I'm going to take my A and stick right here, minus 18J. Why? Because this is the velocity of the person sitting on A. So here, this part was the velocity that the person that was sitting on A saw B to look like. So, what do I do now? Well, the next thing is, hey, wait a minute. This thing is a piston. It's confined to go straight down or straight up. Now, here's where I basically divert from the text. And here's the way I divert. Okay, I have a coordinate system that I've defined that always looks like this. Positive rotation, positive X direction, positive Y direction. So I make the assumption, I know it's wrong, but I'm going to make the assumption that it's going in the positive direction. It could go either way. You know it's going to go down, but I'm going up because it fits with the sign convention. So this means my velocity here is some velocity V going up, J equals to, okay, I'm going to be lazy and do this. Do a copy and a paste, and then move it right here. So I just recopied it. Now what do? Okay, you have two equations, actually two unknowns. Here's how you have two equations. Okay, let me put this. Okay, there we go. Never mind. I got the I component, and I got the J component. Now I can write. Okay, let me do the J as like green. There's your J component. So what I do is I say, hey, I'm going to take all the coefficients of I and write here. I don't have any on the left, but I have this, 2 sine 60 omega AB, and that's all I have. But for the J, I've got the VB on the left. So what I'm doing is I'm getting this. Oh, I just did it backwards. This getting all the blues. I'm sorry, greens. This one, I'm getting all the blues. So in other words, this is the component of the I. These are the components of the J. And then I go in. I go in. I don't know what happened there. It changed color. Maybe I did that. Minus 2 cosine of 60 omega AB minus 18. Did I copy that down? I copied this one, then I copied that one, then I copied this one. I think I did it right. Now, I got two equations. From the first equation, guess what? You can solve that. You can say, hey, wait, omega AB doesn't appear to be rotating. If it's not rotating, then that's 0. And you can stick that in there. And you can say, hey, wait a minute, velocity of B is equal to minus 18. So, first of all, it's going in the opposite direction I assumed, which I assumed it going up. It is going down. And let's look at the philosophy here, just whether this makes sense. At this particular instant, this is going straight down. So is that one. And if they're going straight down and they're going the same value, it's not rotating. There isn't a rotation. So in fact, that's the correct answer. It is going straight down. But I went through the whole math, and I will say that if this were tilted at an angle or something, and the piston were going at an angle, it would not be. Or if the geometry was different, like this was at an angle down to here, say, and then the pin A was here to be, it would not be. That would not be the case either. So there'll be plenty of times that this, all of the different variables, plenty of time for us to find this in which this is not the case. So I think I'm done. That makes sense. And I am starving. So I've got to go get something to eat. Okay, did it work? Yeah. And then